So,
Yeah,
Swapna Achal, I think we can start.
yeah,
Yes,
yeah. Good of. Okay, please start.
yes, good afternoon. So let's start the session. So good afternoon, everyone. I'm Swapna Para, Chair of IEEE NTC Student Chapter at CSIO. I welcome you all to the second lecture of the Electrochemistry webinar series, which is jointly organized by IEEE NTC Student Chapter ACSI CSIO, Electrochemistry, Electrochemical Society of India, and the SRM Institute of Science and Technology, and IEEE Chandigarh subsection. So we are specially honored to welcome our speaker of the day, who is Professor Ramanathan from IIT Madras, and Professor Eid Barkadas, ISC Bangalore, ex-president ECSI, Professor Aruna, president of ECSI, Professor Satish, IEEE branch counselor, CSIR CSIO, and other respected faculty members and guests who have joined us today. Thank you for your presence. So to begin the event, I request Dr. Pooja, who is the advisor of IEEE NTC ECSI CSIO and also governing council member of ECSI, to give a brief about the series. Over to you, ma'am.
Thank you very much, Swapna, for this introduction. So, at the outset, let me welcome our speaker, all our guests, and all the participants to the second talk in this webinar series. So, this webinar series, it was conceptualized as a skill platform for all our young students who are working in the area of or trying to enter into the area of electrochemistry, to basically clear, like understand the technique and understand the fundamentals concept wise, and also how to utilize the this field in the area of energy, including batteries, supercapacitor, even the emerging new areas like metal air batteries, fuel cells, CO2 reduction, these kind of application. And I'm happy to tell that we are getting very good response of this series. Now this is second lecture and we are getting very good registration, so I'm thankful to all the participants for this acceptance. And for today's, we have very renowned speaker with us, Professor Ramanathan. So I formally also thank him for accepting our invitation, and I believe all the participants would get benefited from his deep knowledge in this particular field. So with this, I welcome you all again.
Thank you, Dr. Pooja, for your valuable remarks about the series. Since Professor Aruna is here, so I would like to call her for to give a brief about the series and upcoming events which will be organized by ECSI. So, Professor Aruna, please.
Yes, a very good afternoon to all of you. And at the outset, I would like to thank Professor Ramanathan for accepting to give this webinar. And also, I thank all the organizers for their initiatives. So, as you all know, that Electrochemical Society of India is one of the oldest societies, which is housed at the Indian Institute of Science, and it provides a platform for the students to interact with the experts, and also we give if any consultancy is required for industries on any issues related to electrochemistry, there are experts who give the solutions for their problems. Apart from that, we encourage or we recognize the talents by giving away awards. And you always, I request you to visit our website, ecsi.in. And we are also organizing next month. I think I have shared the brochure. If it can be shared in the group, I'll be very happy. Like, we'll be organizing a corrosion course wherein industrial problems will be addressed by experts. It's in hybrid mode, so interested members can register for this event. Apart from that, we have our annual event, that is the National Symposium on Electrochemical Science and Technology, which we organize every year in the month of July or August. So this time it will be held in August 3rd week at SRM University. I will be sharing the brochure in the group, and I request all of you to kindly take part in this conference and interact with the faculties and also the stalwarts in the area of electrochemical science and technology. So I request you to make use of these two events, and I wish you all the best. And I think now we can we can listen to Dr. Ramanathan's talk. Thank you.
Thank you, Professor Ravna, for your remarks about the upcoming events. Also, we will be sharing the brochures in the emails with the participants. So, it is now my pleasure to introduce today's distinguished speaker, Professor R. S. Ramanathan, who is a faculty member in Department of Chemical Engineering at IIT Madras. He is a pioneer in electrochemical research and has developed technologies in batteries and sensors applications. He completed his PhD from Clarkson University, USA. He has around 22 years of teaching and research experience in IIT Madras as a faculty, and prior to that, 3 years of industrial experience in PDF Solutions, USA. He has guided 13 PhD scholars till now towards their PhD in the field of electrochemistry and has published around 50 plus papers in international journals. His research interests are in understanding the fundamental aspects and in the application of electrochemistry of corrosion, batteries, and biosensors. So, without further ado, I request Professor Ramanathan for his lecture on fundamentals of electrochemical techniques, which is a core analytical method in electrochemistry for energy and sensor technologies. We are truly privileged to have him with us today. Before we begin the lecture, I kindly request all the participants to keep their microphones muted, and you are feel free to ask any question in the chat box, and we will be having them after this lecture in Q&A sessions. So over to you, Professor Ramanathan. You can start.
Thank you for the kind words. So the topic is fundamentals of electrochemical techniques. So before I start, right, I wasn't very sure about what the audience background was, etc. So I have prepared it, assuming that some of them might be familiar with electrochemistry, and some of you maybe just in the beginning. So maybe the audience is varied. So I have prepared in two parts. One part is to introduce you with some background in the electrochemistry. I was kind of self-taught in electrochemistry. I didn't have a regular course. And in the beginning, it was very difficult because there are a lot of terminologies used. And at least at that time, people who are in the field knew what they are talking about. They may not explain it well to newcomer, and the people in the outside the field will struggle and learn. So whatever I could remember, points which were not very obvious to me in the beginning, I tried to list them and kind of assume that maybe some of you may also have certain questions, and if I explain here, it might clear some of them. So first I'll spend some time on the background. With some specific topics, electrochemistry is an ocean. So I won't try to cover everything in 1 hour, 45 minutes, whatever time. The second half, I go to techniques. Again, there are, depending on the application, right, there are many techniques which are specific. Some are general, some are very specific to applications. And I have prepared this in a way that it basically introduces you to the general techniques. I have not prepared like specifically, for example, for battery analysis or for corrosion, etc. So some of these are specific, and general ones I'll introduce here. Maybe at the end, if you have specific questions, I'll try to address them. But right now, what I'm going to introduce you is to a list, after introducing to the background, certain techniques called DC techniques. These are acronyms, you don't need to remember now. In fact, I think one I didn't even prepare here, it's all right. There are some which are called AC. I'll just introduce you in terms of very simplistic, not even 10 minutes, I would say 2 minutes of introduction, because the EAS is a separate topic on its own. So I'll just give you a very brief introduction, but hopefully once you understand the background and understand what are the assumptions involved in applying this and analyzing this, hopefully this will be useful to you. And of course, at the end, just quickly refresh or summarize, right? So this is a picture to indicate we have an electrode, which is usually metal, solid, and then electrolyte, which commonly is water-based, but it can be organic. It can be molten salt. So there are some exquisite ones, but generally it's water-based. When you put an electrode metal in a liquid, something happens. The liquid is supposed to be polar, means if you put sodium chloride, you will have positive and negative ions here in the liquid. And the moment we put the metal into the liquid, some of the ions will come close to the metal. Okay, they line up with this. Let us say in this example, negative ions here come close to this because the metal will give up some electrons and become positive. The solution will acquire few electrons and becomes negative. It cannot really sustain large amount. It's pretty much neutral, but metal is slightly positive, so the negative ions come close to this, and next positive ions kind of line up with this. This is a simple picture, and then you have a region where you have pretty much neutral conditions. So the moment we put this, there is an electric field between the liquid electrolyte. Electrolyte is the liquid, electrode is the metal. There is a voltage difference between these two. So the metal water interface, technically electrode electrolyte interface. It can be graphite in organic liquid, for example, in lithium ion battery. Okay. But generally, I put metal in water-based electrolyte. I would develop a potential. The concept applies to other cases also. And if you imagine, we have positive charges here and negative charges here with a very, very small gap. This is less than a nanometer. It's a very, very small gap. Okay. It looks like a capacitor. So in electrical engineering, we'll draw like this in a symbol and say this is positively charged, this is negatively charged. Of course, we can change the polarity, but this layer is called double layer. One layer and second layer together, this is called double layer, and it looks like a capacitor. So the moment we put a metal, for example, gold in water, copper in water, any of this will form a capacitor-like structure. And the main point here is the voltage developed may be half volt or 1 volt. It's a very small voltage. It's not a large voltage, but the distance is very, very small. So if I say 1 volt in 1 nanometer, it becomes 10 power 9 volts per meter. The field is very large. Okay, so that is one point that I want you to remember. We'll stop there. The next point I want you to remember is, although we are describing this, visualizing this, if I want to measure what is that voltage, I can't really do that. Okay, I'll explain that with some pictures. I'm sorry, I need to erase this. Yeah. So look at this. The left side part is the one I'm describing. Metal is immersed in water and you have positive charge here surrounded by negative charges. Okay. I have to connect this to a voltmeter. One terminal I'll connect here. The moment I put the voltmeter into the liquid, I have a probe that will also develop a layer like this, double layer, which is shown by the small positive and negative. It may be small, large, that we don't know. But the main problem is we do not have a system where the ground probe or any probe of the voltmeter is at the same voltage as the electrolyte or the liquid. This also has some voltage. This also has some voltage. What is measured by the meter is the voltage difference between these two probes only, not voltage difference between this metal and this liquid. This is what we want to measure. But what we measure is from this point to this point. So there is an additional voltage drop. So single interface potential cannot be measured. It's not possible at all. But that is not the only problem. Let us say I immerse zinc in water. Okay, I'll just make up this example. This is not correct number, but just an example. Okay, I put zinc in water, it develops a potential. And although we can't measure, we can just imagine that if water is at 0 volt, if we say that is the reference, zinc may be below that. That is minus 0.2. If I put copper here, and let's say it is 0.8 volt above. These are all our imaginations. This is not what we really measure. This is just what we think. Maybe it's like this. If this is plus 0.8, this is minus 0.2, we will have a battery which is at 1 volt. This really acts as a battery. So I can measure the algebraic sum of these, or algebraic difference, 0.8 minus 0.2. I can get the voltage. That in itself is possible. So it's not some algebraic difference. Okay, full cell potential, it's possible to measure. But it's possible that it was 0.8 above, minus 0.2, that's 0.2 below. It's possible it was 0.6 above and 0.4 below. We don't know how we get 1 volt. We just know total is 1. We don't know whether it's 0.8 and minus 0.2, 0.6 and minus 0.4, or what combination it works. There are infinite number of combinations. In addition to this, there is one more issue. Okay, I'm giving you all this background. I'm just describing problem after problem because a certain solution is used in labs. We want to understand why we go that way. It's not only that 1 volt, I can't assign how much is in the one electrode, how much is in the second electrode. Let us say I apply 1 volt here. It may be 2 other electrodes, just a scenario. I can't even tell if I change the voltage, what happens. Let's say I apply 1 volt in one electrode, I have 0.8 above, 0.2 below. This is how it's distributed. If I apply 1.5 volt now, I can't guarantee you that this has gone down further from minus 0.2 to minus 0.4 and 0.8 to 1.1. That is the additional 0.5 volt is distributed like 0.3 here and 0.2 here. Is that how it is distributed? Or maybe this went down a lot. From minus 0.2, it went down to minus 0.9. And this has gone down a bit. So I can't tell how the 1 volt is distributed. And if I change the voltage, I can't tell how much is distributed to the left side electrode and how much is distributed to the given to the right side electrode. If I keep telling I can't tell this, I can't do this, etc., then what can we do, right? So the problem if I can't tell is, let's say I change the voltage, the current changes. It is not possible to say, okay, in this electrode, so much voltage has changed. In this electrode, so much voltage has changed. That is why the current is changing this much. This is how we want to interpret. But it's not possible if we do this experiment. So what we do as a compromise or as a solution is we use certain types of electrodes called reference electrodes. Okay. They have a property. The property is they will have a fixed voltage. We don't know what the voltage is, but it's fixed. Okay, that means if I use a reference electrode, it is unknown value C1. But if I have 1 volt here, I can tell the voltage here is 1 minus C1. I don't know what C1 is, so I can't tell you exactly what the voltage here is. But let's keep it as 1 minus C1. Now the advantage is if I change the voltage here from 1 to 1.5 and I have the guarantee that this voltage has not changed, then I can say whatever extra voltage I gave here has come to this electrode. So I can ensure that the voltage changes made here will come to M1. But this comes with the issue. The issue is, if I say this is a reference electrode, the C1 will not change. That statement is true only when lot of current does not go through the reference electrode. If very little current goes through it, it will maintain. It is like a buffer. Imagine for people in chemistry background, people with chemistry background, there are buffers, pH buffers, a pH buffer of 4 pH or 7 or 10 or any value. In that, the idea is, if I add slight amount of acid or slight amount of base, the reactions occur in a way that it will bring back to the original pH, right? That statement is true only if you have, for example, 5 ml pH and 1 drop of acid or 1 drop of base will maintain the pH. If you put 2 ml of buffer and 20 ml of acid, the pH cannot be maintained. That is, you can't put large amount of acid or base. Similarly, here, if you draw large amount of current through the reference electrode, it will not maintain C1. This forces us to do one more electrode. I have to add one more electrode here. Whatever current is going through here should be collected through this electrode. Or if current is going in this direction, the electrode should supply current in this direction. That way, all the electrons taken here are pushed back into this without passing current through this electrode. So we use a 3 electrode setup in lab scale experiments with some electrodes as reference electrode. The main reason is we want to say, if we change the voltage here, that voltage change comes only to this electrode and not to the other electrode. For this, we need to use reference. And when we use reference, we are forced to use a counter electrode or auxiliary electrode. So we end up using a 3 electrode set. So this is how it looks. Okay, this is working electrode. This is reference electrode. This is a counter electrode. These are just pictures to tell you how it is. If we control the voltage or potential, and that is related to the current density. We'll see that a little later. But right now, take it for granted that it is related to current per unit area of the electrode. If I have a large working electrode, I'll have a large current for a given voltage. And empirically, not empirically, there is a reason, but right now, again, because in a short time, I still want to present in detail, I'll restrict the amount of information I explain. Some I'll just give it to you. So we need to use large area counter electrode as much as possible. So for those who are kind of doing the electrochemical experiments based on what your seniors do, if your working electrode area is some millimeter square or centimeter square, and you want to use platinum wire as a counter electrode, it's not a good idea. If you don't have enough resources to buy a mesh, it's all right. But if you have resources, you should use a large area counter electrode. Okay. We have 3 electrode system, and that comes with a requirement that you need to use an instrument called potentiostat. Now the name is used very generically. Originally, potentiostat means you can control the voltage and measure the current. Now it also comes with galvanostat. It also comes with impedance. So many of these things, they call it as a potentiostat, or sometimes they call it as a workstation, electrochemical workstation. Basically, they are used interchangeably. requirement of a potentiostat is it has to respond fast. Like we saw earlier, if working electrode passes some current, it has to sense it and draw the current through the counter electrode by adjusting the potential of the counter electrode. So it has to respond fast, it has to be stable, meaning it can't oscillate the voltage. It has to give you a proper value. You have to measure the current and potential accurately. Some of them claim attoamp. Attoamp is 10 power minus 18. I can't even imagine that. But routinely, you would see nanoamps level of resolution. So it has to be accurate. And to give you a perspective, if you want to buy a DC power supply, which can handle only 2 electrodes, DC power supply of 1 amp or 2 amp, you can probably buy that for 10,000 or 20,000 rupee. If you want to buy a 1 amp potentiostat, you will have to spend few lakhs, because it has to satisfy certain requirements, instrumentation requirements. So it's not that everybody knows how to make a good one, and since there are only few players in the market, the cost is high. So this is one part. Another thing which I want you to know is if you're looking at current on the y-axis, current density actually versus potential. If I just use water, this is how it would look. I go to very negative voltage, water will split and give me hydrogen, and positive voltage in that electrode, it will give me oxygen. In between, it will not give me any significant current. But very, very roughly, what I want to tell here is current versus potential. If I use it in a resistor, I would just see a straight line like this going through 0. Here it is not linear. Depending on what species I have, what electrodes I have, I may have current going like this, I may have current going like this, etc., etc. But it's generally not linear. That is the thing I want you to remember. Electrochemical systems are non-linear. And this is the same picture which we saw before. The moment we put the electrode into electrolyte, you're going to form a capacitor. You can imagine this is how the capacitor will look. Now, if you have a reaction, the metal can dissolve and go here. Or let us say copper 2+ ions will come and deposit here. Or some other species can come here, react and give a product. Water can split and give hydrogen. All of them will result in movement of electron through this part. So all of them will give you some current. So we have current passing through a capacitor. If it is DC, current will not pass through. If it is AC, current will pass through a capacitor. You also have a current possibly passing through the reactions. If you have no reaction, then it will be zero current for that. We can put these things together and model in a simplified way, like this box for one electrode, similar box for the second electrode, and in between two electrodes, there is a solution which offers some resistance. This is the solution offering the resistance. Let us say we have the reference electrode and it offers very little resistance. I'm going to use the word resistance in a very general way. If the second electrode offers zero resistance, then you can say the entire system can be modeled like what is shown on the left side: solution resistance and capacitance for the double layer in parallel with some reaction. The reason I'm showing you this is when you apply the techniques, you are going to have a change in voltage, change in current, etc. This is the minimum model we need to keep in mind to understand why the response will come in a certain way. The model can be more complicated than this. Depending on the different systems, you will have more complicated models there. But this is the simplest one. When I change the voltage, let us say I change the voltage I can do it sinusoidally. I can just change the voltage linearly with respect to time. When I do this, the value of derivative dV by dt, voltage is changing with time. It can be 0 if the voltage is fixed. Voltage is constant means the derivative is fixed, 0. Sorry, derivative is 0. If voltage is changing, then derivative will be non-zero. That means if the voltage is, let's say originally it is on some voltage, we increase the voltage slightly, what will happen is this will become little more positive and this will become little more negative. That is like saying I have a capacitor. Let's say there is no reaction. Okay, I have a capacitor. Initially it is at some charge and then I change the voltage, so the charge has increased. But still no other current is passing through, no reaction. This part of the current is called charging current. So it is charging the capacitor, but it's not doing anything else. If we have a reaction where electrons go through this, so when I'm charging, I just pull the electrons from here, more negative ions come here, but no electron goes through from the liquid to the metal or metal to the liquid. Okay, that is charging current. Faraday current is when electron goes either this way or that way, but there is a reaction. That is called Faraday current. These are the two names you want to remember. Man, I think I'm not doing well in time. I'll see. Okay, so few other things, empirical. Okay. Reaction rate constant. If you have a reaction, there is a rate constant associated with the reaction. It depends on the voltage. And I'm not going to tell you how we got this, etc. But the reaction rate constant depends on the voltage in an exponential fashion. So keep that as an empirical fact. The reaction rate, on the other hand, depends on rate constant. It will depend on the concentration of species, etc. So that is going to sometimes depend on the potential exponentially. Sometimes it will vary differently. Similarly, the current and potential not always have the exponential relationship. They will have nonlinear relationship. Sometimes it's exponential and sometimes it's not. I'll show maybe one example or two examples. I'll see. And there is a constant called Faraday constant that we need to remember. That relates, that is basically if I take 1 mole of electron, what is the charge corresponding to that? Okay. So keep this in mind. If all of them doesn't make too much sense now, it's still okay. But you want to remember rate constant depends on the potential exponentially. Take a reaction like corrosion where Fe becomes Fe2 plus with 2 electrons. Okay, this is a rusting. Rate constant is K1. The rate of the reaction is K1 multiplied by the concentration or activity of Fe. This is what we would do in chemistry. The reactant, there is only one reactant. But we know it comes with release of 2 electrons. So if I remove these electrons, if I give positive voltage to this Fe, I'm removing electrons. I'm making this easier. Fe becoming Fe2 plus easier. That is shown by saying K1 will increase with voltage exponentially. If I want to say what is the current associated with this, the current associated with this is basically given by electrons. Okay, and I have made a mistake here. It's fine. The rate R1 tells me how much Fe is going and how much Fe2 plus is produced. But 1 mole of Fe2 plus will give me 2 moles of electrons. So the current will be 2 times this F relates 1 mole of electron gives me so many coulombs. Right? And R1 is the rate. Rate is given as moles per centimeter square per second. Maybe I'll write it here with the mouse, so it's a little ugly, but it's all right. Heterogeneous reaction in chemistry is always written as moles of Fe2 plus per unit area per time. If I take this and multiply by Coulomb per mole, moles will cancel out. I'll get Coulomb per second, which is ampere. Ampere per centimeter square is going to be current density. This is how we relate, this is how we relate a reaction to the current measurement. Okay, so the beauty is using instruments, we can measure small amount of current very accurately. If I want to measure the Fe2 plus concentration in solution, small changes in that very accurately, it's very, very difficult. So instead of measuring the chemical species concentration, I can measure the current and interpret. That is the advantage here. We can do that for copper. We can do that. Here I have written the equation correctly. This is going to be 2 because we know 1 mole of copper corresponds to 2 moles of electron. That is how we do the calculation. Okay. This I have written a little late, but it's all right. Rate is given in moles per centimeter squares per second.
Hello.
And the current density comes out of this equation. Now let's say you have a reverse reaction. Okay. A giving B with some electrons, and B can combine with electrons and give us A. Don't worry about remembering all the things. What I want you to know is this net rate can be written in terms of forward reaction and reverse reaction. One of them depends on the voltage exponentially. The reverse also depends exponentially with the negative sign. So sometimes in books you will see a convention. Forward they would give a negative sign, reverse they'll give a positive sign. Then it depends on how they are calculating the E. It's E minus equilibrium or equilibrium minus E, etc. So sometimes the convention, you have to be careful when you look into that, but don't be worried if you see sign differently in different presentations or different. Basically, it's a notation. This gives rise to an equation called Butler-Warmer equation. So if you have a reversible reaction, you can say the current is exponentially dependent on voltage for forward reaction, exponentially dependent on voltage for the reverse reaction. If I say current in the forward direction is positive, then current in the reverse direction will be negative. That is why this negative comes. This negative depends on the direction. This negative depends on how we calculate the current. Are we going to say release of electron is positive, or are we going to say absorbance of electron is positive, or taking electron is positive? And there are 2 different conventions. One is IUPAC convention, another is US convention. One of them uses normal electrical convention. IUPAC uses that as a positive current, and US convention uses reduction or negative as a positive current actually. So if I take this equation and put some values, okay, and then say I draw I versus E, I on the left side versus E, and let's say I have taken some values for alpha, etc., and some value for this is in fact versus equilibrium. This is how the curve will look like. It will go through 0. It will be somewhat like an exponential curve in this region, somewhat like an exponential curve in this region, and in between it's the effect of both terms here. If I take this and increase the alpha value, I say one reaction, it is this, slightly different reaction, alpha value increases, then the current here will become more, the current here will become less. Okay, so it's not symmetric. I want you to remember that. And you would see sometimes people plotting log of the absolute value of I. We can't take a log of a negative value, so we use this, versus potential. The curve will look somewhat like this. The black color curve here will look like what's shown on the left side, and the red color curve will look lower here and higher here as expected. Now I want to tell you why we do this. The equations are come in terms of exponential, e power, right? But long time ago, historically, people used the graphs. One of the axis will be linear, another axis will be log 10, not natural log based on E. So that is why even now we use log 10. Other part to note is current here goes through 0. If we take log of 0, you'll get minus infinity. In reality, what we do is we get the measurement, it goes to a very negative value, but you don't really going to plot minus infinity here. It's going to look somewhat like this. So if you see the presentations in this, I want you to understand why certain things are done certain way. Okay. Then the last part, maybe I should have kept one for this, and yeah, last part on the background is it's possible to list, okay, can this reaction happen spontaneously? Is it very likely? Is it less likely? Okay, it's possible to say the potential for a particular reaction, or the reaction can happen easily or less likely. It depends on the concentration of these, and there is an equation which describes how the potential varies with the concentration, and this is called Nernst equation. Again, if you're not following it fully, it's all right. Just be aware that it is possible to list based on the tendency of a reaction to happen spontaneously. And the other way, if it doesn't happen, whether it's easy to do it or hard to do it when we give energy. And that is given by what's called standard reduction potential, which, for example, if you're working on zinc air battery, you would know zinc can be reduced. With effort, you can reduce it. You have to give minus 0.76 volt versus some reference electrode. Oxygen can reduce. This gives 0.4. If I want to combine these two, you can see electrons are on the left side here, electrons are on the left side here. I can reverse this reaction and say electrons will be given by zinc. Zinc will become zinc 2 plus and give to electron, and those electrons will be taken up by the oxygen. So it will be 0.4 minus 0.76. Because I'm reversing this, I'll change this sign to opposite sign. So if I use this zinc air battery, in theory, will give me about 1.1 volt or 1.2 volt. I can estimate this theoretically. Like this, you can have many reactions listed. This lithium taking an electron and becoming lithium plus taking an electron and becoming lithium is very difficult. It needs minus 0.3 volt in theory. But it also means lithium can easily give an electron and become lithium plus. On the other hand, fluorine, F2, really likes to take electrons and become fluoride. So it's very easy. The reverse is going to be very difficult. So this kind of tells which is a strong oxidizing agent and which is a strong reducing agent. And this you can get easily in the web, right? You can see, for example, if I take Cu, if I take zinc, I can form a battery. So this, and I can estimate the approximate voltage. So, okay, I'm sorry. It's a background noise. I can't. Just give me a second. Okay, there's not much I can do. I'll see. Okay. Now I'm coming to techniques. I'll see what I can cover reasonably. 10 minutes. Okay, I'll probably skip some and then come. Applications, for example, where we use etc. I think it is all right. The important point is, if you want to use the techniques well, first you need to know what are the assumptions involved in these techniques. Then you can do the experiments correctly and analyze the results properly. Okay. For example, if I want to do CV, how should I conduct it? How should I analyze it? And for that, I need to know what are the assumptions involved in deriving the equations. Open circuit potential, OCP, is one such technique where you just measure the voltage at zero current. You can monitor that over time, and it may vary, it may become constant. If you are using a potentiostat, you can measure the OCP without even connecting the counter electrode, because it is not going to supply any current. And it's always reported versus the reference voltage. If you're having a software, you'll have to specify how long you want to do this experiment and whether you want to measure the voltage every second, every minute, every 10 seconds, etc. You have to specify them and then run. It's one of the simplest experiments to run. Now, what are all the things that affect the open circuit potential? It really depends on, if I take a metal and put it in water or liquid and then measure the potential with respect to reference. If there is any contamination that keeps on absorbing on this, then the voltage will change. The voltage depends on if there is a passivation layer forming on the surface. If the metal dissolves and concentration of the ions next to the surface change, all these things will alter the voltage. So by monitoring this and by having some idea beforehand, okay, this is my liquid, this is the solid, and if I put them here, I think this is what can happen, or these are 2-3 possible things that can happen. Then you can interpret the results in the context. But I cannot put, for example, copper in sulfuric acid and let's just say bronze in nitric acid, and then say I want to compare this OCP with that OCP. That is not going to be easy. We don't recommend doing that. One system, you add an inhibitor, corrosion inhibitor, change in OCP, you might be able to interpret it. Two different systems, don't bother interpreting that. It's not going to be easy. There is a technique called chronoamperometry. Chrono is for time. Amperometry is for the measurement of current. We can say, I want to measure the current in response to a potential step. Right now, the potential is some voltage. I'll increase it or decrease it to this, and I want to monitor how the current will change with time. Every second, every millisecond, record the current and do this 10 seconds or 100 seconds or some value. This is useful when you're looking at electrode deposition. When you deposit, for example, copper, or you're using metal air battery, rechargeable metal air battery, you're electrically depositing zinc from the solution. Depending on how that is done, whether the deposition happens by continuous nucleation of these seeds, or is it happening at an instant nucleation? Deposition will happen continuously, but nucleation, is it happening very quickly? You can find that out by monitoring this. If the response current goes very quickly up, comes down and then stabilizes, it's likely to be instantaneous. If the response current goes gradually and then comes down, that is likely to be continuous or progressive nucleation. So for each technique, I'm giving only a preview. Okay, if you really want to understand fully, you have to spend time reading books. Even though you have YouTube and everything now, still the books have some value. And of course, you can listen to the YouTube videos, but make sure you are listening to the right ones. The advantage of book is generally it is well reviewed and vetted, so you're not likely to get misleading or false information, or it's less likely. In generic YouTube video, the problem is if you get access to a good video, you'll learn very fast and very well. And if you look at a video that is made by somebody who may not be experienced, you might be misled. But you can get the information. We can, for example, in CO2 reduction, we monitor if the current is stable, we expect the behavior to be stable. If the current is changing, we think maybe parasitic reaction may happen more or some poisoning may happen. So if you have the context, you can interpret the results. In battery charging, in lithium-ion batteries, it is done in a mode called CCCV. CC is constant current, CV is constant voltage. So they don't call it as a chronoamperometry, but essentially what they do is CV. CV is constant voltage is chronoamperometric measurement. So sometimes the name may be a little different, but the performance of the experiment is still the same. Chronopotentiometry is similar to this. You control the current and monitor the potential. This again has the reason we want to control the current is if you are looking at electrochemical production of a chemical. For example, I want to reduce carbon dioxide or I want to reduce water to form green hydrogen. In these cases, my interest is in producing the chemical. And I can say if I give so many electrons, I'll get so many chemicals. So if I give a constant current, hopefully I'm getting constant production rate. Okay, this is the reason where we use constant current. If I'm monitoring corrosion, I don't want corrosion. I want to estimate how much will be the corrosion, but it's not in my interest to say I want constant corrosion, I want low corrosion. Then you don't need to use this technique. Okay, so battery charging, like I explained before, is CC mode. It is one part of this. Chemical production rate is related to this, and if it needs more and more voltage, that means power required becomes more and more for chemical production. Green hydrogen, if you want to produce, you want the lowest voltage possible at a large current. So I want a low voltage and constant voltage is the preference. So you can monitor this for a given system. Okay, there are some techniques which are specific to corrosion. One is called linear polarization. This is easy to do. What we do is we change the voltage slowly and measure the current. When I say change the voltage, we first measure the open circuit potential. That is, we just put the material and measure the voltage, whatever happens naturally without any current. Then we say we lower the voltage a little, 10 millivolt, 20 millivolt, and then slowly change the voltage and monitor the current. So 10 or 20 millivolts around the OCP, and then we slowly change and monitor. If I take the slope of the current versus potential, I will get the derivative di by dE. If I take inverse of the value, E by I will give me a resistance, and that is called polarization resistance. So in corroding system, this is a measure. This will not destroy the sample. You can measure this easily, and you'll get some idea whether it is resistant to corrosion or corrosion is happening at a high rate. So it's very simple in analysis, very simple to do the experiment, but you will also get limited information. Okay, which means you will know whether it is corroding much or not, but if it's corroding, you won't know what is the process by which it happens, how can I reduce it, etc. If you want those, you need to do more sophisticated experiments. Little more sophisticated is called potentiodynamic polarization. Okay, it is monitoring again current versus potential, but in a much wider range, plus or minus 250, 300, sometimes even more millivolts here. wider range. Then we can't use the linear equation. You have to use an equation which is similar to what we saw earlier, like exponential, but it's a little different from the Butler-Bowman equation in terms of the meaning. One is for dissolution of metal, another is for hydrogen production. But I'm not giving you all the equations here. You can always look them up. We can use this to estimate how much corrosion will happen. You can also estimate RP. You can also get parameters called Tafel slopes. But again, that's a separate lecture, so we'll leave it at that. One of the common techniques used is called cyclic voltammetry. Okay. Here, what we do is we take the voltage and scan, means we increase at a particular rate or decrease at a particular rate versus time. So imagine I have voltage versus time. There are terminologies: starting potential, vertex 1, vertex 2, number of cycles, etc. If you are doing the experiment, you will have to fill in these numbers in the software. Okay. This example, voltage here starts here, it goes up to some voltage, come back to some voltage, again second cycle go up, second cycle come down. The rate at which it goes up and comes down is called scan rate. Starting potential, of course, is where we are starting. Vertex 1 here means what's the highest voltage, what's the lowest voltage, and how many times we want this to repeat. Okay, we do this and we monitor the current with time. But we don't present current versus time. Instead, we present current versus potential. So we are always recording this. This is how it will look. Current versus potential will go up, come down in the first cycle. Second cycle, blue will go up and come down. It has a funny shape. Okay, people who are familiar will know this. People who are new, this is a funny shape. But this helps us interpret certain things. I want you to know one thing. The electrode has to be stationary. The solution should not be flowing when we are doing this experiment. Okay, these are understood, but sometimes not explicitly mentioned. So people who are not familiar might do the experiment incorrectly. This is used in sensing, biosensing, chemical sensing. It is used in characterizing system. Again, cyclic voltammetry is a separate lecture. You can give a few hours of lectures on it if you want to go in deep. But it comes with some assumptions of how to interpret this, how to interpret the peak value, the width, the difference between the bottom valley and this, the difference between this current and this current. All of this can be used. Why do we get this type of curve? That is because of a compromise between reaction and diffusion. Concentration keeps varying. That is why you get a funny shape here. This contains two types of current. The capacitor keeps getting charged. Reaction happens. Of course, you'll get this only if your system has a reaction. If you don't have a reaction, it will look very, very simple. You will not always get this type of result. This is an example given for one ideal system. It will depend on what reduction and oxidation happens, chemical species, two species, and the voltage we are working with. The gap between these peaks, all these things can be used to interpret. Do we have a chemical reaction? Do we have electrochemical reaction? Combination? Is one of them reversible, irreversible? All those things can be interpreted, but that happens with understanding of the cyclic voltammetry peak interpretation. Okay, I'm going to do one thing now. Let me see. What time is it? Okay, I think I have completed to 45 minutes. See, I have slides. I can talk for more time, but 45 minutes itself in my experience is attention span is not going to be very good for you. It's not you. Even if I'm sitting, I would not have that much attention span. what I'm thinking is, should I pause here and then ask you have any questions, or you want to talk, you want me to talk about anything specific? Is that a good way to do?
There are some questions in between. So if you can just wind up the techniques and
Yeah, that may be better,
what
right? Yeah.
yeah.
Am I still presenting?
Yes.
Okay. Um, so what I would say is, you can use pulse techniques. Pulse here meaning voltage is going to go up, down like this, and monitor current. You can do pulse in current and monitor. These are some techniques that are possible. I'll skip these. People who are working in biosensing might spend some time on learning about this pulse technique, because they come with some advantage compared to cyclic voltammetry. Okay, if you're working in sensing, biosensing or chemical sensing, please spend some time on reading these. Um, the technique which is, I think, very complicated is called impedance spectroscopy. If you're working in science labs and you want to publish, many times the reviewers and editors will ask you to present the spectrum and interpret. It's a good technique, but at the same time, interpretation takes a lot of effort. With that, I will say, in this technique, you would have to use sine waves, measure the current in response to voltage. But it's going to take quite some time to use it well. Okay, that is the caveat that I want you to remember. AC voltammetry is not that common. People, in fact, use combination of techniques, that is in situ. When I'm doing electrochemical experiments, simultaneously can I watch the reflectivity, can I monitor something extra? That way I can understand it better. That is, once you understand the electrochemical techniques, you can combine it with other techniques, but then you need to have the facility, then you can interpret it better. So I'll summarize. So electrochemistry is about processes that happen at the metal or electrode-electrolyte interface. And the advantage of using the voltage current versus time is that you can control the voltage precisely, control the current or monitor the current precisely. These are the advantages. Three parameters, voltage, current, time, are the three parameters. We can use a stationary electrode. I didn't discuss about the rotating disc electrode, but you can control the movement of fluid. There are possibilities. I want you to remember voltage and rate constants are exponentially related. Rates and currents sometimes are related exponentially to voltage, otherwise it is not. You have to be aware of the system to choose which technique is best suited. You'll have to read literature, and that will help you in identifying which technique is best suited for this. So we've seen some of the techniques: open circuit potential, chronoamperometry, potentiometry, linear polarization, PDP, potential dynamic polarization. CV, I think we partially saw. Pulse technique, okay, just we mentioned it, and AS we mentioned it. When you do experiment and analyze, if the assumptions involved in the analysis are more or less matching with the actual conditions, or I should say actual conditions you run it are reasonably close to the assumptions, then the analysis will lead you to the correct interpretation. If that is violated, if you get bad data, it's bad. If you get bad data and you think it is correct data, it's in fact worse. So it might lead you to misinterpretation. With that, I'll stop. And if you have questions, I'll try to answer them.
Thank you very much, Professor Ramanathan, for that informative and engaging lecture, which was starting from the electrodes to electrochemical equations and terminologies, and then the electrochemical techniques, including OCP, chrono, CP, and etc. It was very informative for all the students, I'm sure. And student must have greatly benefited from your talk, and they have must have many questions in their minds. I can see some of the questions in the chat box. Maybe I'll read one by one for you.
Yeah, I can.
Uh, yeah,
Let me re-scroll this and see
okay, that
where
will be
are these.
fine.
Okay, there are
Yes,
several. Okay, voice
yes.
certificate. Okay, so this,
So
what is the
Swapna,
IHP OHP difference between electrolyte and Okay, see,
yeah, please.
IHP is called inner Helmholtz plane. Okay, it is the one closest to the electrode, and OHP is the outer plane, which is right next to that. The closest one will always have the charge opposite to the metal, and the charge is actually pretty much lined up with this, and the OHP is little further next line, and that may not have as many charges. Okay, technically electrode is a material which conducts electricity by electrons. So mercury is a electrode even though it's liquid. Okay, the current can pass by different means. One is movement of electron, another is movement of ions. So I can have a solid electrolyte. Solid at high temperature can permit movement of ions. So electrolyte is something that allows movement of ions. Electrode is something that allows movement of electrons. And in fact, there are mixed electrolyte also, which means they allow both. But generally, for majority of the people, electrode is a metal and electrolyte is a liquid with ions in that. Okay, that is the answer to that. Let me see this. We can't ask doubts. Yeah, you can ask doubts. Yeah. Question answer session. Okay, can you get the record? Can okay, fine. Okay, these are all general questions. Any other counter electrode instead of platinum electrode? Yes, you can use. It depends on the system, right? You can use carbon as a counter electrode, provided that is not attacked, or if it's attacked, the product goes as carbon dioxide outside, and you don't have an issue. You can use gold as a counter electrode. You can use nickel as a counter electrode. Depends on the system you are using. Okay. Why the area of counter electrode should match with? No, in fact, it should be larger. Okay. So area of the counter electrode ideally should be larger than the area of the working electrode. Imagine you are applying 1 volt to the working electrode, 1 volt versus reference electrode. Okay, to the working electrode, plus 1 volt. The plus 1 volt to the working electrode means the potentiostat has to apply negative volt to the counter electrode to give all the electrons into this. How much voltage should it give? All the current taken by the reference electrode should be pushed through the counter electrode. That is all the requirement. If I give large area, I need small current density for the same current. So I have, let's say, 1 amp I have to push within 1 second. If I use a small area, the current density will be 10 amps per centimeter square. If I use large area, it will be 0.1 amps per centimeter square. The current density is related to the voltage. That means the potentiostat has to push the counter electrode only a little if you have a large area. So you're making the job of the potentiostat easier by giving a large area counter electrode. If you make the potentiostat struggle, then what happens is the following. See, we go to the computer, specify, go to this voltage, scan at this rate, etc. We are hoping that the potentiostat is really doing what we ask it to do. But people in the instrumentation, especially if you work with electrochemical systems, if you work with resistance and capacitance, the response is very good. Work with electrochemical systems, you would know that it is not that easy. So you want the potentiostat to do as commanded, and you can help it do it if you give a large area counter electrode. Okay, that would be the answer. Okay, what would be the approximate ratio? If you can give 10 to 1, we don't always give 10 to 1, at least 2 to 1. If not, at least 1 to 1. So it depends on how much you can afford within the cell, how much space you have, constraints you have, etc. Within the constraint, if you give 10 to 1, beyond that there is no benefit. 2 to 1 is still okay. Going below 2 to 1, if you really have to go below that. Otherwise, keep it. And mesh can give you a large area. It's not the geometric area. Okay, I can give a platinum foil. I can give a platinum mesh. The same area, geometric area, mesh will give me more effective area. So you can use a mesh and gain more area. Okay, if it's a homogeneous reaction, you'll have moles per liters per second. If it's a heterogeneous reaction, it is the area that is relevant. That is why it's moles per centimeter square or meter square. That is irrelevant, but moles per area per time. Where the link, okay, you can mail, okay. The centimeters per second because it's dimensionless. You mean the rate constant? Rate constant is centimeters per second. The rate is moles per centimeter squares per second. Okay. Okay. This is good book to read. I think by Bard and Faulkner. Let me write in the message. I think it's called Fundamentals. Maybe it's similar to my title. It's Alan J. Bard, and I don't remember the full name of Faulkner, but that is the message that I would say. That's a book I would say. Then teacher central lecture. Okay, it should be child central. Okay, sorry if no, I do what I can, but let's see. What's the importance of OCP meter? What's the difference between OCP and OCV are same. Just battery people use open circuit voltage, and electroanalytical people will use open circuit potential. LP again, and this importance of LP and PDP. Okay, I can share you LP. So LP basically it is 10 or 20 millivolts around this open circuit voltage, and we take the current. It will be more or less linear. It may not be exactly linear. So I don't have the Tafel equation, but I'll try to show something to explain this. Okay, look at this equation called Butler-Warmer equation. Okay, Tafel equation is somewhat similar, but its actually meaning is a little different, and you will have a different, you won't have alpha and 1 minus alpha, you will have a different notation, different terminology, but it looks similar to this. Imagine I draw this current and I showed you this is how it will look. If you look into this region, very small region, I can draw it as a straight line. That is linear polarization. If I go to a large window, I can't use a straight line. In fact, I have to use the entire equation. So I'll come back to this now. Linear polarization is assuming it can be simplified as a straight line, and it is valid when you use 10 or 20 millivolt. If you use 50 millivolt, it will not be valid. On the other hand, if you use a larger potential window, in fact, I have used the same graph. I shouldn't have done it. It should look somewhat like this. Then I should fit the entire curve to that equation. If it fits reasonably well, then I can say this system can be modeled using Tafel polarization window, Tafel equation. And then again, it's a separate lecture. I don't have the slides for it now. I can show you, I think next month there is a corrosion talk. Maybe at that time I can describe in a little more detail. So if your entire window is taken, then it is unmodeled, you'll get PDP and Tafel. If a small window is taken, then a lot of simplifications are done in the analysis. It's easy, but you'll get less information. I hope it answers that question. Let me come back to this. Four or five electrode system. Okay, that is going to be a little more complex. See, you are applying a voltage. You may or may not exactly apply. That is, potentiostat may or may not be able to apply. So you can have one more electrode to sense what is the voltage that's being applied. That is one way where you can use per electrode. In some system, people use called rotating disk electrode. And in a modification, you have rotating ring disk electrode, where you are controlling the voltage of two different electrodes which are close to each other. These are for specific studies. Okay, let us say I want to produce a chemical and I want to monitor how much chemical is produced at different voltages. I can use two different electrodes and then produce in one. I have a small gap, sense in the other one by controlling the voltage. So like this, there are special cases where you use more than three, but generally lab experiment, 3 electrode is good. During the charging process, what's some material long charging time compared to discharge? Okay. Unfortunately, I won't be able to answer that. I don't have that much familiarity with supercapacitor to tell you what could cause this. Okay, I'm sorry. Use Tafel slope interpreted data for modified electrode rates of degeneration rate. See, first, the problem in Tafel analysis is this. Okay. When I say problem, I mean what I have observed is usually people use the commercial software. Okay. They would draw the lines. Some of the commercial software doesn't tell you necessarily how good the fit is. That is, you're assuming Tafel equation is applicable to that current voltage system. But if the fit is poor, we can't even use that analysis. If the fit is good, then only we can interpret the data. Okay? So let us assume the fit is good. Then Tafel slope, you modify the electrode, the new result also fits well, and then you have Tafel slope. Yes, then you can use corrosion rate. You can use Tafel slope to tell the anodic process is enhanced or worsened, or cathodic process is enhanced or worsened. You can do that. Static condition, how to include dynamic conditions of the electrolyte. So if you want to measure the corrosion rate when the electrolyte is flowing, you have to do the experiment also when the electrolyte is flowing. Then you can do that. Okay. So corrosion cells typically have static electrolyte, but doesn't mean you have to conduct the experiment in that way. You can conduct experiments in rotating disk electrode. You can conduct in other flow cells. It is fine. Okay. Some techniques are return versus reference. You can measure the voltage with respect to reference. Okay. And then you can always recalculate and tell with respect to reference, it's this voltage, but the OCP was so much. Therefore, with respect to OCP, it is. So in the example, I would have given different things, but there is no specific reason to say, okay, for CV, you have to show versus OCP. For a PDP, you have to show versus reference. It's not like that. You can always show versus reference. In some cases, for a particular analysis, it might be beneficial to show versus OCP. So I would have shown you like that. In fact, people measure with respect to reference, let us say, silver chloride, but they can report with respect to another reference like standard hydrogen electrode or reversible hydrogen electrode. So these are not an issue. It so happens some of them I show it as OCP. DMFC observed that some cases cell voltage drop to 0, negative, and increasing the applied current. Okay. So what happens is you are applying a current, you are drawing current, right? The potentiostat, you're probably using a potentiostat or a fuel cell tester or a battery tester. They have the ability to draw current. They also have the ability to give power. Okay. So what happens is, for some reason, your cell has stopped working. So you're not able to, it cannot provide current, it cannot provide power. But since you're telling the instrument, I want to draw this current and monitor the voltage, what has probably happened is, the instrument is giving power to this. That is why the voltage is becoming negative. Okay, so for some, I don't know the reason why the DMFC failed, but for some reason it failed. Yes, once voltage reaches 0, if you want to understand what's going on, you want to debug, you can continue to do the experiment. But if your main goal is to say, I want to know how much power is being given by this, how much voltage is being given by this DMFC cell when I draw this much current, then basically my guess is your DMFC is not able to give this. Maybe the area is very small, it's not able to give this. Maybe something else happened, but you're not going to get valuable power from this. You're supplying power to maintain the current. Zero gap cell. Zero gap cell in electrolyzer is, see, imagine you have a membrane. I'm guessing it is with respect to water electrolyzer or something like that. You have membrane. People used to put a cathode here, anode here with a gap. Then people press the cathode and anode together on the membrane. Now people coat the catalyst on this side of the membrane and this side of the membrane. Zero gap doesn't mean really zero gap. If anode and cathode they touch each other and you supply power, you're going to have a short circuit. You will not have electrolysis, you'll have a short circuit. Zero gap here means minimize the gap as much as possible between the anode and cathode and still maintain the little bit of gap, make it very thin. Reason I want to reduce it is I'll reduce the solution resistance. So when solution offers a resistance, we want to give power, and as much as possible, we want that power to be used to produce hydrogen. We don't want the power to give what is called IR drop or I square R. We don't want to use the power to heat the electrolyte. So we want to give zero gap. Okay. Okay. No, see, HER, how chronometer? HER, okay. See, if you are working in a chemistry lab or materials lab or any lab, it doesn't matter. If you're just developing a catalyst, putting on glassy carbon and measuring how it performs, CV is probably okay. But in real life, you are going to use an electrolyzer, which means a planar system. You are going to operate it either at constant current, mostly constant current, maybe at constant voltage. You have to characterize the electrode. If you ever think this has to become a real system, you can't use glassy carbon, a small 1 millimeter, half millimeter tip glassy carbon, put the catalyst and measure. It's okay to do that in the initial phases, not at the next level. Okay, so chronoamperometry is definitely useful there. Some people prefer to use as a base of working electrode, whereas some nickel foam. Okay, alkaline or acidic. Okay, base working electrode in industry, base electrode is never these. Okay, base electrode is going to be nickel, stainless steel. Stainless steel is kind of a poor substitute. Nickel is good in alkaline. Maybe titanium. So it's in the lab. It's okay to use this as base material, but I can't. Nickel is, if you are going to work with alkaline, nickel foam is fine. I'm not sure why you need to use FTO, ITO. Maybe people in the field will know better. I have some idea about this, and my take is nickel is better. All-on board is hard to understand. I'm not sure what else is there. Okay, there is another book by Bakris and Reddy. It's not meant for technique, but it will give you background. But the disadvantage there is it comes in a very large volume. So it's written in very simple, lucid language. You can understand, like reading like a story. But you need to spend long time to read this because it's a big book. That is one possibility. It won't give you technique, but you will have enough understanding that after reading Bakris and Reddy, if you read All on Board, you will be able to understand. Acidic titanium base is probably needed. Acidic is very harsh condition. Even alkaline is harsh condition, but acidic is very harsh. No easy way. Okay, let me come back to the thing. Are there limitations using two electrode system? See, if you are going to use a constant, for example, if you're going to use a CO2 electrolyzer, if you're going to use water splitting, You have to use a real cell, and real cell will not have enough space to put a reference electrode. All the industrial systems are 2 electrode systems, full cell system, they are not 3 electrode systems. So you won't use a potentiostat. First of all, potentiostat won't give you high current unless you pay a really huge amount of money. You are fine with the normal DC power supply and use 2 electrode system whenever you go to scale up. When you do the labs experiment, 3 electrode system is good. When you go to even medium sized experiment, not even pilot plant, 2 electrode system is going to be necessary. So otherwise, 3 electrode system is quite good. You don't need, you want to connect counter and reference together, you can do that. So small scale experiment in potentiostat with 2 electrode system, you can do that. But basically, your counter electrode platinum mesh will also act as a reference electrode, and that's not a good reference electrode because that will not maintain a constant potential drop. LP importance with slide. Is it importance of meshing OCP? What's the factor? Okay, so LP is for corrosion and OCP is used for a variety of things. If I want to give you, you have to choose a system, only then I can explain. OCP being stable will tell you when the processes become stable, but beyond that, generally giving a description, I don't know how to do that. Okay, sorry. For alkaline acidic is there other substitute? I think mentioned that. Could you spell the book name? Walkris and Reddy. Okay, I don't remember the full book name. I remember the author's name, but you can Google and you will definitely find it. Okay. In addition, any other question? It's already running. I mean, I have time, but do you have time? Hour and a half, right?
Yeah. Hello, am I audible? Yeah.
Yeah.
Yes, ma'am.
So I think it's a very informative and long lecture, I think, and Professor has taken every question and gave answer to. That's really, very amazing to see. So I think we can now conclude this talk. Anything else, Achal? We are left with any? Hopefully, most of the questions are already answered.
Yes, ma'am. All the questions are answered by sir only.
So I think now we will conclude. So I would like to thank Professor Ramanathan for very informative lecture covering all the basic of electrochemistry and the techniques. I'm sure it will definitely help all the students. I can see from the kind of questions they are asking, these are very fundamental questions. Generally, for a beginner, these looks like these are very difficult to understand. So you answered cleared most of the doubts, and I'm sure some of the questions are connected with the next upcoming webinar related to electrocatalysis and battery supercapacitor. So all those doubts will be even more clear when we will have a dedicated webinar on these topics. So I thank you again for your time, and we plan to host in future some in-person workshop for the student participants. So we hopefully would also have to have you in person in this future workshop which we are planning. So thank you so much for your time.
Welcome. Shall I log off?
Yeah. So thank you to all the participants also. Thank you, everyone.
Bye.
Thank you everyone to join.